For those who don't know Guideline Geo and have just turned up to learn a little bit about the seismic method, we're a geophysical equipment manufacturer based in Sweden. We have two product ranges, that's Mahler, which are the ground penetrating radar systems, and ABEM, which are the more kind of traditional geophysics methods. And we have time domain electromagnetic system, the WalkTem. We have a resistivity system, the Terameter, and a seismics system, the Teralock, which is the one that we'll be seeing a bit of today. We have offices across the globe, and these are our kind of main offices that are a combination of technical and sales support teams. Harry and I, who are with you today, we're both actually based in the UK. We're right in the center of this map, but the heart of the company is, of course, in Sweden. So we have our head office in Stockholm. We have our research and development office a bit further north in Umeå, and just short of the Arctic Circle is actually where our factory is in the town of Mahler, where we manufacture all of the systems. We've been around for quite a while. ABEM were actually established in 1923, and they were developing geophysical methods for mapping mineral deposits in Sweden, and gradually they morphed into a manufacturer. Mahler were an office of the Swedish Geological Survey, interested in electromagnetic methods, and gradually that morphed into GPR. And so we've had been working in parallel as equipment manufacturers, and then in 2013 came together under the Guideline Geo banner to offer kind of complete solutions. So that's a very brief history, and of course we're looking forward very much to 2023 when we can celebrate our centenary. Then, for those of you who don't know me, my name's Jimmy Adcock. I'm the product manager for the ABEM products, and I'm a geophysicist by training. I worked as a surveyor for a long time and then joined Guideline Geo about 6 years ago. Started as an applications engineer doing technical support for customers and sales staff, and then delivering training, workshops, that kind of thing. And then last year during the summer, I moved into the product management role, looking after our current products and deciding where we go next. So that's enough from me. I'm now going to hand over to my colleague, Harry, and he's going to take you through the rest of the webinar today and tell you a little bit about himself. So I will stop my camera and allow him to take over.
Thank you, Jimmy, and welcome everyone. Let me just turn on my camera. There we go. So my name's Harry, and I am by training an engineering and environmental geophysicist for the past 7 years. This blank screen you see is because I recently only just started at Guideline Geo. So I'm yet to get out and get some nice pictures. So hopefully next year we'll get onto that. So yeah, at the moment, I'm just trying not to get too comfy sat behind a desk. Short overview. Jimmy covered a few of these points, but the webinar is designed to give an introductory overview of the seismic refraction methods. As Jimmy said, it'll take about an hour to take, and what we'll do is start by looking at a few historical landmarks and how advances in technology have allowed the method to be continuously useful as a dynamic tool for geophysicists and the broader industry alike. There'll be an outline of some important physical concepts and how surface refraction methods work in practice. The presentation will also talk about the practical aspects and considerations required when undertaking refraction surveys. And then there'll be a case study at the end. And as Jimmy said, if you have any questions throughout the webinar, please put them in the chat box. So to start with, much of our understanding of the deep structure of the Earth owes a great deal to seismic refraction methods. For example, the MOHO, which defines the crust mantle boundary, and the Earth's core. Developments in the methods, along with advances in technology in the early 20th century, such as the electromagnetic geophone, paved the way for commercial oil exploration and intense research over the following decades. The installation of seismic networks further expanded our understanding and would help to build a repository of data invaluable to research. Advances in computing led to the application of numerical methods and data modeling, such as seismic refraction tomography. The manufacture of smaller portable digital seismographs enabled the methods to be applied far more extensively to near surface. These advances in technology allow for cost-effective solutions to a host of near-surface investigation targets widely adopted worldwide. And the model M84C, just as a side note, is, as far as I can find, the first and earliest seismic refraction tomography model produced. So just looking at the last 30 years, there are numerous applications for refraction in the world of engineering, and just a few of them would be groundwater modeling, derivation of engineering parameters, repeatability assessments, stratigraphic mapping and depth to bedrock, fault identification, amongst some of them. So over the past 30 years, seismic refraction methods have been used extensively for engineering, mineral and petroleum investigations. The timeline below shows some iterations in digital seismographs that ABEM have produced over recent years. In hand with the development of newer, more advanced processing methods, advances in technology increasingly allow for the design and manufacture of lower noise, higher precision instruments, and these allow users to increasingly target smaller signals and apply the methods to new and interesting targets. So, starting with the theory, there are three main types of seismic wave. First, we have the P wave or primary wave, and these travel fastest because the wave motion and the energy transfer are in the same longitudinal direction. Note that the particles within the block are compressed and then return to their original shape and size. P waves can be utilized for both reflection and refraction seismic surveys. Then we have S waves, secondary or shear waves. These travel slower because the wave motion and the energy transfer are transverse to the direction of travel. Note that the particles within the block are not subject to compression, but are displaced. S waves are more commonly used for reflection surveys, however, are also utilized by refraction surveys, especially where engineering parameters are required. The slower velocity equates to a shorter wavelength and therefore potential for increased resolution. And then finally, we have surface waves. Rayleigh and Love waves have slow traveling and complex motion. The particles are both deformed and displaced during the wave propagation. Also, these are the fastest attenuating waves, and they propagate much shorter distances than the P and the S waves that accompany them. What we have here is a seismic trace with time, and then on the left we have the source, and you'll see that the first arrival with time is the P wave. Now, as we say, generally used for refraction. The next arrival is higher amplitude but slow moving, and that will be the S wave, which are more commonly used for reflection surveys, although they are interchangeable. And then after that, we have the surface waves, which are the highest amplitude. Sorry. Okay, so it's important at this stage to define some ways in which we represent the seismic energy. If the source is entirely within a homogeneous material, the energy will propagate out in all directions at equal speed. Leading edge of this expansion is referred to as a wavefront. We often simplify drawings of seismic motion by reducing it to a single ray path, shown by arrow, and that's drawn perpendicular to the wavefront. So this is how we will show our seismic waves. So let's talk about some of the physical principles that govern seismic refraction. The first one is Snells Law. So when a wave travels from one material to another of different properties, the wave can change direction and velocity. And the amount of deflection experienced by the wave is related to the level of contrast in physical properties between the two materials. The term for describing this phenomena is called refraction, and Snell's law defines how the incident and refracted waves are related to the velocities of the materials through which they move. And this is important because it allows us to make predictions about the material and the wave based on some measurements. As this picture shows, we can see the effects of refraction in everyday life. In this case, light waves enter water droplets. They slow and bend, splitting into a spectrum of light, which we see as a rainbow. However, these laws are not limited only to light waves. Snell's law can be applied to the ground below us too. Acoustic waves can be refracted at subsurface interfaces when the density and elastic properties of the ground change from one material to another. For example, changes in geology. However, this raises the question, if the wave coming from the surface refracts and then continues its path downwards, as you might expect, with a change in angle, then how would we measure it at the surface? To do this, we have to make use of a phenomenon called critical refraction. And this is when an incoming wave hits the boundary at just the right angle, that the refracted wave travels along the boundary, all the while it radiates energy back towards the surface through what are called head waves. They are these waves that we detect using receiver arrays at the surface and allow us to map the geology beneath us. So to help us to see how critical refraction works, let us rearrange Snell's law and solve it for our refracted angle so that we can examine what will happen to rays as we increase our angle of incidence. Let's take a subsurface with a layer 1 velocity of 2,000 meters per second and an underlying layer of 4,500 meters per second. If we input waves at increasing angles of incidence relative to the vertical or normal, the equation produces larger and larger angles of refraction in order to maintain balance between the ratios within the Snell's law equation. In this case, at 26.3 degrees, however, that angle of refraction reaches exactly 90 degrees relative to the normal. And at this point, the wave travels parallel to the geological interface, where it travels at the velocity of the second layer, which is 4,500 meters per second. And as it does so, it radiates energy outwards in all directions as head waves. And these are the waves we measure at the surface. If you enter any value greater than 23.3 degrees, in this case, it would return a mathematical error because the inverse sign of an angle cannot exceed 90 degrees. The physical reality of what's happening is that waves arriving beyond 23.3 degrees are not giving up, but they are just being reflected instead. So we need some basic elements for a seismic refraction survey. One would be a source to produce the seismic wave that goes into the ground. Then we need receivers that will detect those waves as they return. And then we need an instrument to record the wave patterns, which we call a seismograph. Just before we look at the recorded data, there are some general rules to consider when surveying. Here's an example of a 24-channel setup with 2 cables forming the spread. This is a common survey arrangement. So we have the seismograph in the middle and then 2 cables, each with 12 channels on either side. Although every case is different, in practical terms, 1/3 to 1/5 of the cable's spread length, so that's the total length of the array, is a good estimation for the achievable depth of the survey. Geophone spacing is very important if the site is likely to have thin layers of material, that are important to the survey aims, then resolution will be further improved by using higher frequency sources and geophones. 2 shots will help to identify whether the ground layers dip rather than being horizontal, as we have in our simplified examples. If you then add more shots, we will produce a more accurate model with better lateral resolution. As mentioned, it is only the first arrivals that need to be identified. Each vertical line on this plot represents the response from one geophone over time, with 0, the point at which the source generated the seismic energy, at the top. The yellow circles highlight the first arrival on each trace, i.e. at each geophone. If the slope is constant, it shows that a series of arrivals have traveled at the same apparent velocity to increasingly distant geophones, and therefore this would indicate layering. In the central shot locations, the top 2 layers are visible, as you can see. layer 1 and layer 2. But then if we look at the off-end shot, so this is a shot taken off the end of the spread away from the geophones, you can then see layers 2 and 3. Layer 1 is too shallow. But the off-end shots allow you to map the deeper refractors. So this is called a time distance graph. And what it's going to do is plot the time taken for the appearance of the first arrival at each geophone on the vertical axis against the geophone's distance from the source on the horizontal axis. The point of impact is at a known distance and the recording time starts when the impact is made. And this is called time zero. So as the wave travels outwards from the source, a portion will travel directly along the ground towards the geophones. Meanwhile, a portion will travel down towards the next layer. Where it hits the critical angle, the rays will travel along the faster refractor and radiate energy outwards. At some point, the refracted energy will overtake the direct wave, and this is called the crossover distance. At this point, the refracted waves will be the first arrivals, and because they travel faster, the slope of the graph being plotted is going to change. It used to be the case that utilizing a combination of intercept time, slope, and crossover distance, layer velocities and thicknesses could be manually calculated. This is through a relatively simple method of modeling the seismic energy path and employing elements of Snells Law and trigonometry. But how can we be sure that layers are horizontal? Plotting the time of the first arrival from one shot at each of the geophone positions produces a graph like the one shown. If horizontal layers are present, lines from the opposing shots, so the shots that are taken at either end of the spread array, will produce a symmetrical time distance plot, which is what you're looking at now. However, if the layers below the ground are sloped, then the two travel time plots will not be symmetrical. Here's a dipping refractor, so this is what we're talking about. In this case, the apparent down dip velocity will appear too slow because the second leg is longer than the theory suggests. So the equations are assuming that the energy has traveled a shorter distance in the recorded time and therefore must be traveling slower. Similarly, the apparent updip velocity is too fast in this instance because the second leg is shorter than the theoretical model expects. Now let's consider the time distance plots for multiple shots within the spread. So here you have a separate line for each shot. And note that what shots 1 and 7 are off-end. So this is the shot, this is the line described by the arrival from the middle shot. And then shot 6 at the end describes the arrivals from here. And then we have an off-end shot there. And you'll notice that the off-end shot traces more of the deeper, flatter refractor that is shown in blue than the center shots, because it has more time to reach the refractor that's deeper and then propagate back to the surface. So this is an important reason for having a range of shot positions through your spread. And then next, the inversion software is going to create a model that's based on these curves and compare the theoretical response with the recorded data. And then it will keep adjusting the model until the two sets of results, theoretical and recorded, match to within a preset tolerance. A low error value between the theoretical and actual results tend to indicate a more reliable model. So let's look at some common source types. First, we have the sledgehammer, and that's cheap and simple, but limited on its reach in terms of depth. A polyurethane hard plastic strike plate will give a better source pulse than a traditional metal plate. And then we have a buffalo gun, which uses shotgun shells to create a small explosion with the barrel of the unit pushed into the ground. These are lightweight and portable, so good for sites with limited access where a little extra energy is needed. Vibration units allow a range of frequencies to mix good penetration with excellent resolution. Please note that in addition to the vibratory sources shown, larger are available with potentially much higher depth ranges. And then we can look at the powered weight drops. These provide excellent repeatability, which gives good results when stacking to improve the signal to noise ratio. There's a broad range of sizes and energy outputs available. Another method for potentially creating a high-powered source is explosives. However, this will clearly be limited in many countries by legislation surrounding the purchase, storage, and use of charges. And then finally, marine sources vary in size, ease of deployment, frequency, and depth capability. This is a small, what we call boomer type source, and is good for nearshore surveys. Then we have the geophones. The construction of a geophone is a cylindrical coil of wire wrapped around a magnet, which can freely move. As the geophone moves relative to the magnet, the current is generated, and the current is proportional to the acceleration of the magnet through the wire loop. A range of geophones may be used. We have spiked, which are good for soft ground, tripod, which are good for hard surfaces. So that's the one with the orange top. And then we have the free axis, which measure different components of the ground motion. And then this graph here, it shows the response pattern from a 10 Hertz geophone, and the 0.3 damping in the dark blue line is showing the resonant frequency at around 10 Hertz. Geophones must be damped, or the geophone will continue to oscillate after the ground motion stops. Damping reduces sensitivity, so the amount of damping is a trade-off between controlling oscillation and maintaining sensitivity. Damping is varied by placing a shunt resistor in series with the resistor coil, and most manufacturers choose a value of 0.7 of the critical damping value, which, as you will see in the image, produces a flat response to frequencies that are higher than the natural frequency. So the 0.7 damped response is the kind of teal line that's below the blue one. So now, if we're looking at the survey design aspects and our choice of source, we need to consider cost, repeatability, speed, and portability. These are all important factors in commercial surveys. Hammers are lowest cost and suitable for a variety of near-surface applications on land. So a good place to be in is to ask, will this provide enough energy, or will I need a more powerful source? If the depth to the target is great or the overburden highly attenuating, then a larger source may be required. Larger sources are typically less portable, more time-consuming setup-wise, and more expensive, so it'll be important to consider these limitations. In addition to considering the overall energy output of the source bandwidth affects the ratio of energy useful for refraction and reflection relative to the ground roll. Note, for example, in the bottom figure shown above, that Thermex, shown here, produces almost 1 order of magnitude more energy than the 136 kilogram weight drop, but only incrementally more reflection/refraction energy. So you also want to make sure that you're getting the most for your money. Also note that in the above example, that when grouping weight drop in general, that they are producing noticeably more refracted/reflected energy and less ground roll in relation to the smaller grouping of explosive sources, despite the fact that the total energy output is similar. So I just group those now. And once we've chosen our source, we can move on to choosing our geophone for the particular site that we're working on. So one thing to consider is that the Earth acts as a low-pass filter, meaning that as waves travel increasing distances from the source, higher frequencies are attenuated more quickly than the lower ones, as shown by the green line. For refraction surveying, we seek the largest amplitude response possible for waves first arriving at the geophone. So in the example shown, the 14 Hz geophone shown in orange reaches a higher output at lower frequencies than the 100 Hz geophone, despite the overall higher response of the 100 Hz geophone at higher frequencies. The low pass filter effect of the Earth means that generally the 14 Hz geophones will outperform the 100 Hz geophones unless the source to receiver offset is very small. Note also that this effect will apply increasingly as offset between the source and geophone is increased. The larger the source receiver offset, the higher the filtering effect the Earth has, and the more low frequency signals will be preferentially transmitted. So the general rule is a larger array means a lower frequency geophone will be preferable. A couple of points on data collection and good practice that will help avoid things from getting messy on site and ensuring you get the best data possible. So one is to keep cables on one side of the line to avoid loops where possible in the cables. Have receivers and sources as well coupled to the ground as possible to ensure that the signal can be transmitted with as little loss in energy as possible. Wind and rain can act as significant noise within a shot record. It can sometimes help to bury or place weighted pots on top of them to minimize these effects or wait for conditions to improve. Pre-triggers can be preset on the seismograph, and these will allow you to assess the repeatability of your source, which is a good method of quality control. Areas of standing water or soft ground can also cause poorer coupling or even noise within your shot record. So where possible, it is always good to try and avoid such features. So here's an example of a basic workflow for seismic refraction processing. And the aim, as you put your workflow together, is to set out a repeatable and reliable procedure for turning your raw shot records into final velocity sections. So the first stage, the pre-process, this is where we undertake quality control of shot records and we filter them ready for further analysis. This usually includes things like checking that the array geometry matches the field records, and trace normalization, which makes sure that the maximum amplitude of each trace will be equalized to account for attenuation of the signal with distance from the source. And then applying filtering to the records. For example, if there are high frequency noise due to wind, then this can be filtered at this stage in the time domain, or a repeating signal due to power lines could be filtered in the frequency domain. Next, we would identify first breaks within the shot records and mark them. This is called a data pick, and they are saved as separate text files containing only the time and the distance data, which can then be read into the software for the next step. I find that a good method of approach when picking seismic refraction data is to pick first only the clear and most confident data to carry forward, because otherwise layer assignment can become uncertain. Shot records can always be reassessed later, but it is always better to start from a place of greater certainty. In the case of dipping refractors and topography, it can at times make layer matching more tricky between shots within a spread. And this is all the more reason to have confidence in the initial pick data. Next, you want to load your time and distance data into the software and manually select the breaks in slope, which correspond to the layers within the Earth. So at this point, you're using your interpretation and your knowledge of geology and the physics behind what's going on to match up the breaks in slope with what you believe are the changes in geology. And it's probably the most critical step that can be tricky if there are limited data points, noisy data, or where, as said previously, topography varies in relation to the refractors. These factors can change the apparent velocities of the travel time curve, and if carried forwards into the inversion, they can potentially lead to poorer results. The processing software also needs to know the height of your geophones and sources relative to each other so that the computed travel times are correct. It's easy to imagine how data collected on the slope would impact the results if this were not taken into account. So these data must be included before the inversion. So the principle of reciprocity states that the measured travel time between source and receiver are independent of the direction of travel. This means that we can look at travel times from different shot points or rays that have followed the same path in both directions. And this is an easy thing to do when you have multiple shots along a symmetric seismic array. Where significant differences in travel time exist, usually more than a few percentage, we know there is some error likely in the data picking. This is a great QC step to do before the inversion, as it will allow you to go back and adjust or remove erroneous data picks and improve the initial model before the inversion. When you run the inversion, a computer will adopt a starting model based on the number of layers you have told it exist. For the data, it will compare the travel times required for the model against the real data and calculate the amount of difference between the two. It will then move the model, compare the two again, and determine if the error is increasing or decreasing. We will then know which way to iterate the model, with the aim being to reduce the difference between the two as quickly as possible for the parameters set by the user. If that difference between the model and the data is higher than the user has said is an acceptable amount, it will perform another iteration, and it will keep doing this until it meets the stopping criteria, which is usually a maximum number of iterations, or error, which when it drops to within an acceptable limit, it will stop. Next, performing ray tracing can be used to calculate synthetic travel times or ray paths used to produce the model. It can be used to highlight areas where ray coverage is relatively lower than in other parts of the model. Such areas indicate where the model reliability is also lower. Often models will not show variable uncertainties in these different regions by default, so this can be an invaluable tool for assessing your model and when making your subsequent interpretations. Once you are happy with your errors and you have taken your ray coverage into account, you can carry forward your model as the final model to use for interpretation. So there are published velocity tables for different geology types, such as this one, but the velocity can also indicate the state of the rock. Weak, poor quality rock will have a lower velocity than solid and weathered bedrock. As this figure shows, with the large overlap between materials, velocities are not unique to the given geology or the structural state, and good interpretations will include other sources of information such as geological maps, borehole logs, or other geophysical datasets. Despite this, it is often possible to make some broad best guess interpretations. And then we have a few limitations of seismic reflection. So we have potentially blind layers, which is where layers are not thick enough to be seen, so they fall below the resolution limit of the array that you have set up. Or we have hidden layers, where a subsurface layer reduces in velocity, which means that you cannot get a critically refracted angle. And then as a result, it will overestimate the depth to the next visible layer. And then finally, we have the 3D effects, which is if you have buried subsurface features off to one side of the array, and for which you're producing a 2D slice through the ground, what we're not taking into account always is that the wavefront is 3D and it's moving out in all directions. So if there are objects off to the side, you might get anomalies produced by that. Next up is the data example. So over to you, Jimmy.
Thank you very much, Harry. That was really good, really informative. Yeah, so as Harry says, I'm just going to finish off with the easy bit and show you a case study from a seismic refraction survey. This particular one was from Norway, and excuse me. Okay, from Norway. It was a combined rail and road upgrade project. And so, as you can see, quite a long project covering a huge amount of ground. And a major part of the ground investigation toolbox was using refraction seismics. And they were doing survey both in sort of a marine setting. So they had the Terralock set up in a boat, and they had what we call a hydrophone string. So rather than geophones sat on land measuring vibrations, you have hydrophones within the water column measuring pressure change. So they were doing both land and water-based survey to then be able to understand the strength of the bedrock beneath, because there were a lot of zones where tunnels were required, and those tunnels were either beneath the water bodies or actually through the hillsides. So this is just a very small example of some of their refraction data that they collected. Obviously, there would have been quite a lot on such a big project. But what it's highlighting are sort of quite neatly in one data set are sort of three of the things that you might be looking out for when you collect this refraction data. So we have the data plot in the top here with the color scale representing the velocities. And in this instance, the reds and the whites are the faster velocities, and the darker blues colors are the really slow velocities. And from a perspective of trying to define how, let's say, strong a rock is, how competent the bedrock would be, then what we're looking for is something that has a higher velocity, because that means that it's probably not fractured, means it's good solid rock, the vibrations move through it very, very quickly, so nice and dense. And so the things that they could do with the results from this survey were they could identify where the bedrock lay. So that was pretty simple. It was the point at which you have a sharp velocity contrast from the lower velocity overburden, the soils, the glacial till, soft, very slow. It gives as the energy tries to move through it, slows it down. So you have a sharp contrast between that and the bedrock beneath, which is much higher velocity. So that was a relatively easy pick for them. And then they could look for other zones where within the bedrock itself, there were unusual changes in velocity. So they could identify a zone of weakness where the velocity has dropped, and this is most likely a zone of fracturing. And so rather than a nice solid dense piece of bedrock, you've got something that is crisscrossed with fractures. And so again, that material can shift as the seismic energy moves through it, and that slows the progress down. So they would highlight this as something that needs further investigation. And also discontinuities, things like jointing, fault lines, they can also be identified where you have these strange patterns in the velocity where you wouldn't expect to see such a sharp offset in velocity. And you quite often see this where you have either a big fracture or a fault line, that the rock either side of it is then fractured and weakened, and therefore has a lower velocity. So obviously this is used in combination with traditional invasive ground investigation. So what you're able to do is to then say, we need to target these areas that we get a better handle on exactly what's happening to the bedrock there. So speeds up that process of investigation. Okay. I think that's the end of the webinar. So I hope everyone's found that interesting. I haven't seen any questions come in on the chat whilst we've been going through this. But if there are any questions, feel free to either pop them in there now, or alternatively, you can contact us afterwards.